So in today's video, we're going to conclude our discussion about set theory. This will include some further remarks about the axiom of choice. In particular, I'm going to describe that relationship that I wanted to do in our last live session, the one that shows that the well-ordering principle implies the axiom of choice. We're also going to discuss some of the history of the axiom of choice, and we'll finish off by talking a bit more about the Banach-Tarski Paradox. This will probably include a actually very rigorous statement of what is meant by the Banach-Tarski Paradox, instead of the sort of loose version that I gave in our last meeting. Okay. So to start, remember that the well-ordering principle says that every set can be well-ordered. And a well-ordering, let me remind you, is just an ordering such that every subset contains a least element under this order. So let's review some sets that do have a well-ordering and other sets that maybe don't have an obvious well-ordering but can be given a well-order if you try hard enough. The first one is the natural numbers. This one is very easily seen to be well-ordered. You just have to use the standard order. The main reason why this works is because every point is sort of spaced apart and the smallest number in the natural numbers is given as 0. But Z, Q, and R under this same standard order are not well ordered. For example, if you think about Z, the whole of the negative integers is not bounded below, so it has no least element. But if we import the order from N onto Z by the means of a bijection, so remember we constructed a bijection between the naturals and the integers, and this showed that N was equinumerous with Z. So if we take that this order from N and bring it to Z with this bijection, then we can see that Z can have well ordering. It's just that you have to define the ordering a different way. And with the same strategy, remember that since Q is countable, it is in bijection with N, we can actually do the same trick. So that actually gives us well orderings for N, Z, and Q, just from cardinality. However, the same trick fails for R because, as we saw, there is no bijection between N and R. If there was, R would be countable. So actually, nobody knows a well ordering for R, and nobody actually knows a well ordering for any set whose size is greater than R's. And this is why the well ordering principle is so hard to accept, because it basically stops working intuitively after the size that is the integers. So we'll prove that well-ordering implies the axiom of choice by first considering an alternative to the axiom of choice, which we will call ACP from now on. And what we mean by ACP is just the axiom of choice, but in its power set form. So here's the statement. Let M be a non-empty set and consider the power set. Remember, the power set is the set of all subsets of M. Then the powered set form of the axiom of choice tells us that there is a choice function that takes us from this thing to this thing. So this is the power set, but minus the empty set. And this here is just M, the set that we started off with. And it just has to have the property that it acts like a choice function. So H of whatever subset I choose inside my power set has to actually belong to that subset. So all of this may seem a little dense like last time when we first started introducing the axiom of choice. So let me go ahead and distill that for you. It's very simple. Essentially, all you do is you take your set M and it has a bunch of subsets. And what the power set form of the axiom of choice says is that every subset of M has an element that I can choose. Okay. And I should note here that the subsets have to be non-empty, because notice that our choice function explicitly excludes the empty set. So really, this is just saying that I can pick an element from every subset. This is actually equivalent to the axiom of choice. And what I will do is I will demonstrate one way of the proof. Remember, in order to prove this, we have to prove that ACP implies AC, and we also have to show the other equivalence, or the other implication works as well. So AC implies ACP. So I'm going to prove the harder version, which is to show that ACP implies AC. This means I get to assume the power set form, but then I have to prove AC from that. So here's how it goes. we have to show that given a family of non-empty sets, that one can assign each member of the family an element of itself. This is just the original statement of the axiom of choice. You give me a family of sets, and I can pick an element from each member of that family. So let F be this family, and we're going to try and use the choice function that is given to us by ACP. So here's a fact that we'll have to use. If M is the union of F, the power set of M consists of all possible subsets of elements of F. Okay, so let's read into this a little bit more. Think about the sets in F as baskets. And what we're doing when we take union of F is that we're just dumping all their contents on the ground. And that's just the collection of everything in F. Okay? Now, what is P of M then? P of M is the set of all subsets of this union. So in particular, any subset of UF is going to be an element of the power set of M. Okay? Because remember, the power set consists of all subsets. In particular, notice that we can retrieve every set that was originally in F. Remember, or F is the family that we're trying to show has a choice function. And actually, every set appears as a subset of the power set of M. Remember, M here is just the union of F. So I've drawn actually a schematic to show you basically what we're doing. F is my family, right? That's a family that's been given to me. Here I've drawn 3 sets. And then I form union of F, and this is what I call M. Union of F is found by just dumping all the contents of all the sets on the ground. So here I have some balls, I just dump them all on the ground, and this is my set M. Now, what does the power set form of the axiom of choice tell me? Well, it tells me that if I take every single subset that is not empty, okay, so here are some subsets that are non-empty, it actually, notice here that these two are subsets. But actually, when I collected these things as subsets, they actually mimic elements in my original family, right? So this is what I mean by every set that was originally in F can be retrieved as a subset of the power set. So here I have elements of the power set, but in particular, these subsets are actually the same as the sets that I started off with. Now, why is this important? Well, the axiom of choice, the power set form, tells us that for every subset of this union of F, which we called our M, we can take the power set, and the power set consists of all these guys, right? Now, with each element in the power set, I can pick an element from that set. So in particular, notice that that means I can choose an element from each of these guys. And that's exactly what I needed to show in order to show the axiom of choice. I just needed to show that from each of these individual baskets on the left here, I can just go ahead and pick an element from that. So really, the formal way of writing this is that if we just focus on the subsets that are identical in content to our original members of F, we find that the function g restricted to F is a choice function for F. Now, what is g? G is the choice function given to us by the axiom of choice power set form. So really, the power set form is a lot stronger than what we really need. The power set form tells us that for every one of these non-empty subsets of union F, I can go ahead and pick an element from them. But I don't need a function defined on all of those. All I need is a function defined on these 3. Basically, every single guy that was a subset or an element of F to begin with. Right? So because I can do that by the power choice, the power set form, I get the choice function for free. I just have to restrict it to every single subset that looks like something that was originally in F. So that concludes the proof. And with this out of the way, we can actually perform a logical maneuver that allows us to prove the thing very easily. So we do well ordering, right? And we show that this implies the axiom of choice power set form. Now, I told you that these two the axiom of choice and a power set form and AC are equivalent, right? So I just actually proved one way. So this is what we proved. We proved this direction. We proved that the axiom of choice power set form proves AC. But actually, I can get you as an exercise to do the other way around. So why does AC imply the axiom of choice power set form? Okay, and we actually don't need this other direction in order to show what we wanted to show, because once we get two implications in a row, this will actually lead us to conclude that WO does indeed imply AC. So this is what we just did. All right, so let's do this. So why does well ordering imply the axiom of choice power set form? So what we're allowed to assume when we're doing this proof is that every set can be well ordered. Okay. Now to prove ACP, what do we need to do? Well, we need to have a non-empty set M, and then we need to show that there's a choice function on the sets PM minus the empty set. So every subset, except for the empty set, we can define a choice function that just picks an element out of that subset. So what does WO tell us? It tells us that M can be well ordered and that each non-empty subset has a least element. Okay? And now what I want you to think about for a moment is to think about how this fact right here, the one that we're allowed to assume, allows us to actually choose an element from each subset of M. Okay, so think about that for a second. Remember, WO tells us that every non-empty subset has a least element. All we need to do is choose an element from every subset of M. Well, the answer is that we can just use the choice that is given to us by well ordering. Remember, well ordering tells us that every non-empty subset has a least element. So actually what I'm going to do is for every non-empty subset, let's just pick that least element. Well ordering tells me it exists. I don't have to actually say what it is, but it does exist. I've denoted it as min A here for any particular subset of M. And remember, a subset of M is just an element of the power set. Of course, we're ignoring the empty set here. Okay? So this gives us actually the choice function from Pm minus the empty set to M. And it satisfies the property that H of A is an element of A. Okay? So notice how quick that proof was. All we had to do was really just interpret what well ordering tells us, right? This is basically the crux of the proof. Because well ordering allows us to have a minimum element, we can just choose that minimum element, and that gives us the proof of ACP. So that concludes the bulk of the proof work that I wanted to do today. To conclude basically our whole saga on set theory, I'm just going to talk a little bit more about AC, talk about some history and some of its consequences. So I did make a big deal about WO being very non-intuitive, but it turns out that it was actually the motivation for developing AC. And this was Zermelo's idea, by the way. He wanted to show WO because WO is very important in Cantor's work, especially when exploring infinite subsets of R. So already we know of a couple of infinite sets, N, Z, Q, and R itself. Those are all subsets of R. But there are also many more subsets of R. For example, we can think of all the open intervals. Here I wrote down 0, 1, which is the set of all numbers that is between 0 and 1. Right? So as you can see, there are many, many, many infinite subsets of R. This one right here is infinite, and of course there are infinitely many open subsets. Okay? Now, one might look at this as a bit of a paradox, because we have AC, which is somewhat obvious and easy to accept, and WO, which is not at all obvious and can be quite difficult to accept. And the reason why this is so annoying is because WO, the thing that we wanted to prove, is not provable through any of the other 9 axioms, and neither is AC, but AC for some reason is a lot easier to accept and yet is equivalent to WO. And this is quite concerning and it bothered people for a very long time. And then it came to a point where people had to make a decision because no one was making any progress on this decision. Do modern mathematicians have to ignore or do they accept AC? And the answer, as we'll see, is mostly yes. The reason why is because many crucial facts in every field of math rely on some sort of proof done by AC. Some examples that pop in mind are things about calculus, measure theory, topology, and we will actually get to see one of these. Linear algebra. Now, linear algebra is actually probably the topic, linear algebra and calculus are probably the topics that are closest to what you're studying right now. In fact, you'll do a little bit of linear algebra in grade 12, calculus and vectors. The other result that I wanted to talk about is the result by Girdle and Cohen. So this is not something that they worked on together. It was two independent results. That's funny because the result is that AC is independent and consistent with respect to ZF. What does this mean? Well, it just means that the ZF axioms, remember those 9 axioms that I talked about, they cannot prove AC, and you also cannot disprove AC from them. So in other words, AC is totally separate from ZF. You can either choose to accept it or you can choose to not accept it, and logically it makes no difference. So in this sense, we get this conclusion, which is that acceptance of AC is just a matter of taste. It's a matter of what you want to prove, what you want to assume to be true. And the big problem, probably the biggest problem out of all these, is the Banach-Tarski Paradox. The problem arises because we got this really unintuitive result from AC, one that's even worse than WO, one that should not even make sense in a perfect mathematical world. So let's go over this one a little bit more carefully. We have a ball, a 3D ball. It's a solid ball in the 3D space R3. I've drawn it over here and I've shaded it in to indicate that it's solid. We can partition the ball into finitely many subsets. How many is finitely many? 5. Why is it 5? Don't ask. You can check the proof if you wanted to see that. But in any case, once you have divided the ball into these 5 subsets, which can be then moved by translation and rotation, that's really important because that means it doesn't actually change the size of anything in here. We can produce 2 balls of the exact same size as the first. Now, what is meant by same size? This is actually specified in measure theory. And of course, we're not going to go into a deep course in measure theory that would allow us to actually parse through this proof. But the point is to understand that this paradox is the cause of a lot of concern for people who are trying to decide whether or not to use AC in their mathematics or not. It's concerning for 2 reasons, actually. The first one is that it massively undermines our intuition about size, volume, and etc. But maybe that's not too bad. There are some results in measure theory that are non-intuitive by their nature. But perhaps the most concerning portion of all this is that the proof is non-constructive. It doesn't actually tell you how to do this splitting. It only tells you that you can do it. It tells you that you can do it if you split the ball up into 5 subsets. But to construct those 5 subsets is very difficult. Of course, you can imagine that just cutting the ball in 5 like nice pieces is not going to work really well. Actually, in order to do this construction that Banach and Tarski came up with, you have to divide the ball into these pieces that look extremely ugly. How ugly? Well, as ugly as fractals. So the current attitude in math to AC is probably best summarized as follows. It's essential everywhere. No one can get around that. However, its tendency to prove counterintuitive results like the Banach-Tarski Paradox, those things cannot be exactly ignored. So actually, the attitude is now that you want to try and prove things assuming AC, but a fact that relies crucially on AC is going to be met with some suspicion. And actually, it's a big thing to try and get proofs of theorems without the use of AC when they have already been done with AC. Actually, it turns out a lot of really important proofs can be really nicely shortcut if you assume AC. They have a bit more complicated proofs if you don't assume AC, but nevertheless, it's quite important that you can do some of these proofs without AC. This means that it relies only on the original 9 axioms, and we know considerably more about the original 9 ZF axioms, and we have a considerably better feel about their, their acceptability. Okay, so this concludes everything that we were going to talk about in set theory. In our next meeting, we will be doing topology, and in the next video, we will actually be doing algebra. which sounds completely unrelated to anything that was advertised in this program. But as we'll see soon enough, algebra plays a really crucial role in topology, and I hope we will all enjoy this, this new discovery together.